Hi, I'm Teacher Thomas. Welcome to math class. Today's topic is functions, transformations. We're going to work through an example from A-Level 9709 Pure Mathematics 1, June 2020, paper 13, question 3. In each of parts A, B, and C, the graph shown with solid lines has equation y equals f of x. The graph shown with broken lines is a transformation of y equals f of x. State, in terms of f, the equation of the graph shown with broken lines. The three types of transformations you can expect on A-level are translations, reflections, and stretches. In A, we see the relationship between f of x and the transformation as a reflection through the y-axis. So any point on the function here, I'll take the point 2, 1, is transformed to negative 2, 1. What I observe is the y values are the same. The x value sign has changed. So I want to get the same output, the same y value for the opposite x. Thus, y equals f of negative x. Looking at B, we see that all points on the broken line are above f of x. We also notice that it's not the exact same shape. There is a stretch that's been applied. If we look from the point where x is 2 on the original function, we go up 1, that is a distance of plus 1 to get to the next point. Over on the left, if we start where x is 1, we need to go up 2 to get to the point on the broken line. In relation to the x-axis, the stretch factor we can calculate as the distance from the x-axis to a point on the original function relative to the distance from the x-axis to the transformed point on the corresponding function. From the x-axis to the low point on f of x, I go up by 1. For the corresponding point on the broken line, I go up by 2. And I can see the same relationship with all of the points going from f of x to the transformation. This is a stretch, a vertical stretch of 2. The correct notation is y equals 2 times f of x. For any given x input into the original function, the y output in the transformation is doubled. C. We can observe that we have the same shape, so there's no stretch. We have the same orientation, so there's no reflection. There must be one or more translations. There are 2. If we take the low point on the original function and compare that to the low point on the transformation, we see that we need to go from an x value of 2 to an x value of negative 2. We're moving left by 4. And we have a y value going from 1 to negative 2. We're moving down by 3. The representation in our transformation, to show x moving left, we want to use addition. To show y moving down, we want to use subtraction. The y movement is intuitive. We're decreasing the y, therefore we use subtraction. The x movement is counterintuitive. As we move left on the x-axis, the values are getting smaller. However, the way the function input-output works, we want to show the opposite sign in our transformation. Thus, our transformation is y equals f of, we're going to adjust our x term, x, again, plus, I'm reducing the x, so I use the plus sign, counterintuitive, but that's how it works, x plus 4. That will adjust x outside of the brackets. Minus 3 will adjust y. And now every point on the original function will be transformed with a move left of 4 and down of 3. This completes our requirements, and this completes the lesson on functions transformations.